start the session for the afternoon, which has about 4 talks. And to start with, it's my pleasure to invite Florian Douetteau, who is CEO of a really cool website, Dataiku, which is dubbed Excel for Big Data. It does a lot more than Excel. It basically put a lot of data, does all the data analysis for you, it visualizes it. Florian, tell us more about it.
Thanks. And thank you for this great introduction. I wanted to talk to you today. So actually, I'm teaching about data science a lot. And so I wanted to just take a step back and take a look at the big trends I see in this particular space that we call data science, which is actually a mix of lots of concepts, meaning like big data, machine learning, visualization, business, and so on, and see what are the kind of questions that I find interesting. Because when I speak about data science, depending on the actual audience, I might have either like big pictures to say that data science is great and that we will change the world with data science. Or I can take a more math perspective, like data science is complex. It's very complex. That's what you need me or great tools to help you do data science because you won't be able to do it on your own. Or even I can take another perspective, like the daily life of data people, which is about cleansing data, normalized data, waiting for big computing jobs to end, and stuff like that, which is actually the daily life of lots of people maybe in this room, I don't know. And so, well, obviously, depending on the audience, when you are on the west of the Atlantic, it tends to be that this one is like more appealing. When you are in France, obviously, this one is kind of great because, you know, French people, we are kind of pessimistic. But, well, it depends. But overall, I would say that in terms of trends and interesting subject I find in data science, you've got this question of infrastructure of technology, where we do believe that lots of things is commoditized, meaning easy to get, but it's also lots of moving parts. You've got this question of data, which is big and available, but it also means that it's accessible to everyone. You've got smarter models and machine learning techniques, but it also means that they can be tricky. You've got highly personalized and unique products you build with your data, but it also means that they are very fragile, maybe, and volatile. And you need to hire new people with great skills, but it also means they will be hard to hire, maybe. So let's take that step by step. And so in terms of technology and infrastructure, so actually as it was mentioned, I actually started a company called Dataiku 2 years ago, but before that I was kind of consulting in terms of data science and big data. And 3 years ago, I did this awful slide, which was about this particular land I called back then Technoslavia, which is, well, the whole idea is that when you want to do something in data today, you basically have like 6, 7, 8 domains, like machine learning, high volume storage, NoSQL, SQL kind of querying, drilling in the data, visualization, statistics, data cleansing and workflows and stuff like that. So you've got 6 or 8 domains, technical domains, and maybe you've got like 4, 5, 6 different good technologies that you can use for each of these domains. And most of them will be free or open source or both. And so what it means is that you don't, well, imagine you've got like 8 domains and 5 good technologies. You don't have like 40 possibilities in terms of architecture. It's like more 8 power 5, which is like 400,000, I think, possibilities for big data architecture, which is a lot of different possible architecture. So you've got more technologies, and then maybe time to explore it. And so I think that one thing which is key, that lots of companies actually invested a lot in choosing the right technologies, having strong opinion on what they should do regarding big data infrastructure. So some of them, for instance, they said that we want to follow a cloud-based infrastructure and just do everything on the cloud, on one particular cloud. Some others have taken the completely opposite direction, building everything internally and so on. But whatever happened, I think that the big trend in data science and data today is that, well, first, if you never invest too much in terms of data infrastructure and thinking about infrastructure and data and everything related to that, and just because there are lots of moving parts, you probably need to be very ambitious and have very strong lines in terms of software architecture and impose that to your team if you want to be successful as a company. Meaning you need to have big data architecture as a strategic part of your company. It must be part of your image if you want to be able to hire the right people. You just can't say, I don't know what I want to do. You need to be able to say that you've got a strategy here. Another interesting story, this one related to data. And for this one, I will take the perspective of a startup company. So I happen to mentor maybe half a dozen data-driven startups these days. And I definitely see a pattern, which is that when you are a startup company, meaning you start a business, you're not a big company, your problem, if you want to build a data-driven product, your number one problem is actually the data. Meaning you do need some data to do big data. Meaning with no data, you cannot do big data. And so you've got different strategies for startups in order to handle that one particular problem. The first one is the grasshopper strategy. So the grasshopper, so it might sound funny, but only to French people, but the grasshopper is a very optimistic animal, which, and the grasshopper who sings all summer long, can be very well deceived and hard to feed when winter is coming, as you might know. So grasshopper is an optimistic animal and would wait for open data to be available and build added value on top of open data. And the grasshopper startups just get the data that is here and try to build value on top of it. So it's highly risky because open data might not be available as expected, but it works. You've got the spider strategy for startups, which is basically about building your own network of sensors or trackers or devices. And typically, a spider startup would give away the sensor or trackers or whatever for free, and for let's say 1 year, 2 years, and then try to monetize on top of it. So obviously, that's a very costly kind of strategy because you need to build your network, but it's highly effective and proved to be very effective in the digital advertising world. For instance, Google is a spider startup, typically, which then monetized very well on top of an existing network of web data and so on. And so the key question is, spider startups will behave in the new IoT kind of world with physical sensors. And then you've got Fox, the Fox strategy for startup. And so basically the Fox will hunt for a big group or a big company which already has a big data asset, but also a big data problem, not able to actually solve it on its own. And so typically the Fox will make the big company pay a small fee, probably not free because it would sound suspicious, but a small fee. It will solve the problem probably as a kind of a online software as a service solution. It will internally build a predictive model on top of the company big data asset. And with this model, it basically has a product that you can put on the market for maybe all the competitors of the big company he just hunts. So that's a Fox strategy. And so this one is, well, it works very well for B2B, but it means lots of tricks regarding anonymization, intellectual property, and so on. But my key question, but I think my takeaway on that is that whenever you are a big company or you have a data asset, well, it means that data is accessible, but it's not only accessible to you, meaning lots of people will be able to get access to this data or data which is very similar. And so you should not put all your kind of strategic position on the fact that you're the only one having access to a particular data, I think, today. So a third big trend is related to models, meaning I'm meaning specifically machine learning based models. And so for this one, let's just, for instance, consider the situation of an insurance company. We are in an insurance company, so that's, I think, a good example. And so an insurance company actually has different questions related to customers, like questions related to advertising, to pricing but as a discount, pricing as a risk for insurance product, questions related to frauds, and each of those questions actually as it's a different problem, but and with a different, very different term and horizon in terms of actual realization of the events related to the forecast you want to make. Like advertising, it's more a question of seconds or minutes. Should that display an advertising for someone, and is the guy likely to click? I will know if the guy has clicked or not in a matter of a few seconds, or even milliseconds sometimes. Pricing and discounts, it's more like related to, well, a few days, meaning it's like someone is looking for an insurance product, and it will take like 2 weeks or 3 weeks for him to actually choose which company he will actually buy the product from. And you've got pricing as a risk, where it's about your actual risk. So here it's over years. And you've got fraud, which is more likely around weeks or more, depending on the situation. And so for each of those, you've got a model, which are actually, today, in most situations, completely independent. So that's the perspective of the use cases. Then you've got the perspective of the technology, meaning the algorithms. And so here, the big trend is that the algorithms continuously improved. We went from decision trees to recursive neural networks, passing through ensemble methods and boosting methods and so on in the last 2 decades, in terms of what are the mainstream algorithms actually used by people tackling the most complex problems. But the thing is that I think, and that's my personal experience, but of course it's, I guess it could be highly discussed. In every data science problem you have today, at least half of the problem or the added value comes from your ability to actually specify the business problem and the business goal, and the ability to have actual data. Then you've got lots of the value coming from domain-specific or use case-specific feature engineering, meaning understanding your data in order to build the right metrics to use for the model. And then the value coming from a particular algorithms, meaning a particular algorithmic technique to train using machine learning, is only an incremental gain on top of that. And speaking about feature engineering, here again in the last 2 decades, we went from a way of using mainly and only expert knowledge to derive new features, to more kind of brute force approaches, computing automatically lots of variables, like getting from a 10 or 20 columns dataset to a few thousands columns datasets. That's the big trends from the last decade. And today, lots around graph analytics, natural language processing, vectorized text domains, and so on. And that's a big trend. But if you put together those two perspectives, I think that what is interesting from the perspective of a large company having lots and lots of different problems related to data science, is that depending on what kind of problem you want to solve, you would have possibly different algorithms or strategies. Like if you've got something with a very long-term realization period, like risk, you would tend to have a need white box kind of approaches, possibly using linear methods and not so advanced feature engineering. If you had something which is very short term, you probably can rely on data a lot and have more black box approaches. And so at the end, within a single company, you have like black box approaches and white box approaches. And so today, it tends to be different people working on white box approaches and black box approaches, and that do not realize that, meaning do not realize that maybe they have to work together and work on the arbitrage or possible correlation or possible incompatibility between these different approaches. So my particular takeaway on this is that there will be maybe a new job in very large companies in the next 5 years, which would be about having an overall strategies for handling all the models within the company and assuming black box or white box approaches depending on a particular problem, which is, I think, a job which is not so well defined today. Then, in terms of product, so, well, we talked many of the speakers over these 2 days actually spoke about Internet of Things. So I will speak also about Internet of Things, but quite briefly and not as well. But yeah, obviously we live in this great world where all the devices we will wear will have some part of predictive models inside of them that will help them take the good decision based on historical data and so on, more or less. It can be an app in your phone, it can be your watch, it can be something in your home, it can be your car, and so on. Okay. So the obvious generalization that everybody is thinking about is that, well, in order for those devices to be really smart, you need to actually merge all their data and behaviors together and have like devices that actually understand the decision made by the others, which is actually fairly difficult to do, and one order of magnitude more complex than the things that we are doing today in terms of machine learning or complex intelligent systems, I think. Because what we are doing to do today in terms of kind of continuous learning advanced architecture more or less looks like that. It's like ad hoc architecture when we try to handle the fact that you need to, at some point, use all the historical data to train a model and understand something, and also take real-time data in order to take real-time decision and possibly make incremental changes over an existing predictive model. That's more or less the way real-life applications works today. And so there is a huge gap between this kind of crude designs that do exist and this kind of not so crude designs, but with a big white hole in the middle, I think. And so I think that the big trend in data science is that, well, even if it looks like kind of science fiction today to do data science, just because there is science in the world, it will get even more complex in the upcoming 5 to 10 years, just because we will actually try to build distributed smart systems, which is actually a very, very hard problem. Then, last topic is about people. So this is not a screenshot from a Dataiku office, so even if we are 50 and that we are hiring, we are not that big yet, so we are a small and happy startup with a small human open spaces. But so regarding data science, so generally speaking, I think that in terms of data, you've got this huge kind of translation from we work on descriptive analytics, and so we use the word business intelligence, to we work on predictive to prescriptive analytics, and we use the word data science to describe the actual work we do. And so in those new data science teams, you've got new titles for people, even if it's the same people with the same skills, like data analyst, data engineers, data architect or big data architect, and data scientist. And obviously there is it's a huge question for companies how to build those teams, manage them, scale them, actually hire the people, and so on. And so here, I think a very important question is to know whether data scientists actually exist. Meaning, obviously they exist, meaning at some point I use the title data scientist for myself, so yeah, I do believe that data scientists exist. But the thing is that the myth of data scientist is someone which knows the business very well, knows text very well, yeah, highly creative, passionate, ambitious, and so on. He really wants to tackle the problem of big data. He knows machine learning pretty well, hyperparameters, feature engineering, deep learning, and so on. But it also can learn and understand the business and all the business concepts within your particular company. But also, it might be, just because of that, it might be very hard to hire him, find him, manage him, and maybe he wants to take your job. So my own personal statistics is that back in 2011, I think I knew 15 people which were data scientists, and I think that 85% of them has actually funded a startup or a CTO or CEO somewhere, just because they wanted to take the job of the guy above him. So a question for companies, I think, and this slide has a TITRAS title, which is strange, I guess, is that, well, you can also imagine having like data analysts and the job of the data analyst would be to discover patterns and fight against the entropy of data and dig in the data to find what the ground truth in your data and so on. And data engineers, whose job and mindset would be to make things work. It's actually very hard. I'm not talking about skills, but just mindset. To have people which know and want to make things work, and people that want to find the truth. Meaning, doing both at the same time is really very hard, whatever the domain. And so, a question for company is: can you want to hire one analyst and one engineer and find a way to make them work together effectively, or would you hire 2 data scientists? And I think that's a good question in terms of organization. And that was my last slide, actually.